right, good morning again, everybody. Welcome back to the DAC Pavilion. It's my distinct honor this morning to have Professor Marilyn Wolf of the University of Nebraska in Lincoln as our Tech Talk speaker this morning. Before Professor Wolf gives her talk on co-design for edge intelligence, perception, control, and computing, I'd like to bring up Gi-Jun Nam, the current president of the IEEE Council on EDA, who will present her with the 2022 IEEE Leon K. Kirchmeier Graduate Teaching Award. Gi-Jun?
So, hello everyone. I'm Gi-Jun Nam from IEEE CEDA, the president, and it is my honor to be able to participate in this celebration today and to represent the IEEE Board of Directors to present the 2022 IEEE Leon Kirchmeier Graduate Teaching Award, one of the most prestigious technical field awards. Sponsored by the Leon K. Kirchmeier Memorial Fund, this award recognizes inspirational teaching of graduate students in the IEEE field of interest. Originally, IEEE President Dr. Ray Liu was supposed to be here, but I'm representing him because he couldn't make it. It is my pleasure to present the award to IEEE Fellow Marilyn C. Wolf for creating a community of researchers and practitioners in embedded computing through education, outreach, and research. Professor Wolf is the Elmer E. Koch Professor of Engineering and Director of the School of Computing at the University of Nebraska, Lincoln. As a driving force in embedded systems, education, and research, Professor Wolf has enabled the proliferation of computers contained within physical objects that are critical to today's advanced applications. These computers power our world across many disciplines, from transportation to healthcare. She has enabled a new generation of researchers to conceptualize, build, and validate modern embedded computing systems through her influential textbooks, high-impact conferences, and mentoring of graduate students. Professor Wolf wrote one of the first textbooks in the field, Computers as Components, Principles of Embedded Computing System Designs, as well as High-Performance Embedded Computing, Applications in Cyber-Physical Systems, and Mobile Computing, which is geared specifically to graduate courses. And I remember these two textbooks, by the way. She also helped to create many of the technical meetings and technical publications in the field, including Embedded Systems Week and the journal Design Automation for Embedded Systems, providing essential forums for graduate students. On the behalf of the IEEE Board of Directors, it is my great pleasure to recognize and share my sincere congratulations with IEEE Fellow Professor Marilyn C. Wolf, the recipient of the 2022 IEEE Leon K. Kirchmeier Graduate Teaching Award. Professor Wolf, please come up to the stage. Very beautiful medal over here. Thank you very much.
Thank you so much. Thank you so much.
Thank you.
Thank you.
Thank you.
Boom.
Thank you very much. Can I
Yes, thank you. Thank you very much. It's a real pleasure to be here with so many friends. I first attended DAC in 1981 in Nashville. And let me throw in a recommendation that Nashville is actually a really fun town to have DAC in. It is a real pleasure, in addition, to be back together after 2 years of not being able to see each other in person. I want to say thank you to my graduate students. and I have learned so much from all of them. These are the students for whom I have advised or co-advised dissertations. I've of course worked with many more graduate students over the years. I am so proud of all of my students. They have done so well. And this is also the perfect opportunity for me to thank my advisor, Professor Robert W. Dutton of Stanford University. Some of you know Bob. I was hired into Bob's group in the spring of 1978 as a sophomore. I was a scruffy, introverted kid. My first job was to make Supreme tapes and send them out to people who wanted them. That spring, Bob put me on his brand new ARO contract on VLSI CAD, and along the way, through my undergraduate years and my graduate years, Bob taught me how to be a good researcher. He taught me how to be a good advisor. He made me understand that being an advisor is close to being a parent. And he, along the way, introduced me to some of the most important scientists and inventors of the 20th century. And I will always owe him a debt. So, in the great tradition of technical talks, I changed the title. Fine. Okay. I want to do three things today. First, give you some background and give you my perspective on why my students and I are thinking about some of the problems we're thinking about today. And then I'll tell you about two different pieces of work. The first one is by my student Krishnamurthy, along with Professor Justin Bradley, on perception and control. And the other is by my student, former student at this point, Deep Samal, and Professor Shaibal Mukhabhedi at Georgia Tech and I on flash Lidar. So let me test this new microphone. Still works, right? So the traditional concerns of embedded computing are known as SWAP, size, weight, and power, right? Size is important because it affects the overall packaging. Weight is important in a lot of things. It's particularly important in vehicles because you have to drag that weight around with you. And of course, power consumption, the associated heat are important in a whole bunch of systems. As a side note, let me point out that even the Arduino, which is by today's standards a modest system, is not that small, right? I remember the IBM PC, the original IBM PC. Do you remember that? 640K RAM? Okay. We thought that was great back then, okay? These systems are not data centers, but they are quite capable. But our job is to squeeze the most out of them. Okay, so I'm interested in computers that deal with the physical world. Okay, control is an important aspect of that. We're thinking about vehicles, both air vehicles and ground vehicles, but control systems happen in all sorts of different embedded applications. A lot of, say, internet applications, right, are interested in one set of metrics, and throughput is an important metric. For control, we need a different set of metrics. Okay? So, throughput measures how many instructions you can finish. Okay? Pipelining is an important technique for throughput. In control systems, we are interested in latency, okay? And in our case, the latency through the sensor, okay? Pipelining doesn't really help you with latency. We care about from when you get the data to when you finish processing it, how long does it take, okay? So, we have been thinking about how to analyze perception systems for vehicles in order to better understand how to design them, right? So why is latency important? Because we know from very basic control theory that in the case of analog sensors, phase delay through the sensor, if it's big enough, can drive the system to instability. Okay? That is, you have too much delay in the perception, it's going to give the control system wrong data, and the control system is going to make wrong decisions. Okay? So latency is clearly an important characteristic for a computer vision system that's going to go into a control system. How much latency is tolerable? Okay. Neural networks, as we all know, are the technique used today for computer vision. There's been a lot of work in computer vision for several different types of applications. Okay. And there is quite a bit of work on neural networks at various levels of computational effort versus the accuracy characteristics. So these are several different neural networks here. And there are at least 3 different things we can look at in order to understand the computational cost. One is depth. That is how many layers in the network. One is the size of the convolution windows, and another is the number of parameters. Okay, so this table compares in the number of layers in these different networks, convolutional and fully connected layers. You can see that there's quite a bit of variation. Okay, although even the simplest networks are not incredibly small. So convolution is a key operation in these neural networks. It offers embarrassing levels of parallelism, which is good. However, the fact that we have multiple layers means that there are data dependencies. Okay? So we cannot finish that second level of convolution until we have results from the first one. Okay? There has been quite a bit of work on efforts to take a neural network and to optimize it. There are 2 major methods, I think. One is sparsity, that is basically zeroing out certain coefficients, because we know multiplying by 0 is easy. Okay? The other is numerical precision, using lower precision neural network, lower precision arithmetic, going to integers, in some cases, even binary neural networks. And these are some examples of different research efforts that have looked at those techniques. Okay? A lot of these techniques assume that the required accuracy is fixed. They say, I'm going to optimize the network while maintaining the given accuracy, or within 1 or 2%. Okay? But if we're designing this neural network as part of a larger control system, does that really make sense? Okay? Should we look at what accuracy is required for the control? Now, this thing has, there we go. Okay. Right? So what do we care about in a control system? Well, you'll see in our application, we're using tracking as the task we want to do. How well do we track? Right? That's what we actually care about. Okay? So why don't we ask ourselves, what kind of accuracy do we need for the components in order to achieve our system goals of, for instance, tracking accuracy? Okay? And once we understand that, perhaps we can make trade-offs between the implementation of the perception and its accuracy, and that there was the effects of that accuracy on the control system. So this is ongoing work. We continue to work on this, but I'm going to show you some of our early results on this. Okay? And why is it that we can think about this as a co-design and as a trade-off space? Well, it's because feedback control is really good. Okay, it works really well. It's very robust to all sorts of variations in the physical plant and in the sensors and all sorts of things. When I was at Bell Labs, out in the lobby, they had the copy of the New York Times that Black wrote the feedback equation on while he was taking the ferry to work. It is one of the most important inventions in all of engineering history, and let's take advantage of it. Okay, so we decided to pick a problem that would allow us to explore this design space, and that is drone-to-drone tracking. Okay, now this is actually a practical problem because, for example, if you've got drones that are entering controlled airspace, you want to chase them down and so forth. But it's also a very nice abstraction of some of these questions that we've been asking ourselves, right? So you've got a chase drone, you've got a target drone. If the chase drone is perfectly tracking, then that target drone is always in the middle of the frame, and it's always the same size because it's the same distance away. Okay? It requires precise control. How much precision in the perception do we need to achieve that? Okay? And the costs of computation come to the fore because this is a flying example. Okay? We're worried about weight, and we're worried about power consumption, not just for the platform itself, but because every erg of energy we spend on computing is an erg that we cannot spend keeping the bird in the air. Okay? So Krishna set up this pipeline in order to perform some experiments. He's also done some flight experiments. I won't show those to you today, but the simulation setup allows us to do control experiments, which is of course important. So we're using AirSim, which is a widely used UAV simulator. It does control steps, simulation steps, puts out a frame. Okay? We grab that frame, run it into a neural network. Okay? Do the perception task. It gives us a bounding box. We then do some calculations to transform that into the form that's needed for the control system. Give it to the control system. It comes up with the control action that's needed, feeds that to AirSim for the next step. Okay? And so now we can modify the neural network. We can run at different sample rates and so forth. So for these experiments, we looked at two different neural networks. One is faster RCNN and the other is SSD. Now, faster RCNN is faster than its predecessor, but it is somewhat slower than SSD. It also, in traditional metrics, is somewhat more accurate. Okay, so this gives us an interesting trade-off in accuracy versus computational costs, and as we'll see more directly in sample rate. Okay? So sample rate tells us how fast the control system can update its actions. This plot shows you the tracking error of this simulated chase. The y-axis is errors in meters, the x-axis is second. And this is done at 3 different sample rates, 1 hertz, 2 hertz, and 3 hertz for RCNN. Okay? That's as fast as RCNN will go, and given the setup that we have, given the machines we're using to run the neural network, that's as fast as we can make it go. And the speed of the chase drone is 5 meters per second, a simulated 5 meters per second. Okay, so 1 hertz is supposed to be the blue line. It's not there. That's because it didn't work at all. Okay. 2 hertz is the orange line, and you can see that the up and down arrows are where the system temporarily lost the target and then regained it, which happened several times until at that blue dot it completely lost. Okay? At 3 hertz, you see it lost and regained tracking several times, but it ran almost twice as long before it lost track. Okay? So 3 hertz is not quite fast enough, really, to do the tracking at this speed, right? SSD same basic parameter setup. This runs faster on our implementation, and so we're looking at 5 hertz, 10 hertz, 20 hertz, 30 hertz. The blue line is 5 hertz. You can see that it's losing and regaining track quite a few times, but it's maintaining tracking. Okay? So the shape of this curve comes from the fact that the target is maneuvering in that middle portion of the timeline, right? So you would expect the chase plane to be able to need to correct a little bit. So that's why you have this hump shape in the error curves. Once we get up to 10 hertz and above, the performance is pretty much the same. At 10 hertz, there's a little bit of occasional losing, but they're pretty much the same. The overall error in tracking is about the same. Okay, so we see that the control performance saturates with sample rate. Okay, so why push it to run at some extremely high sample rate if it's not going to make a difference in the control system? Okay. On the other hand, there seems to be a fairly sharp cliff at the low end. If we start to reduce the sample rate, then at some point the control performance goes bad very quickly. Okay. So this table shows for RCNN the sample rate in the columns and the velocity of the target on the rows. Clearly, the faster the target is going, the higher the sample rate you would expect to need. And at this low end of the sample rate space, you can see that this gives you a generalized version of what we saw before, that at 5 meters a second, it really doesn't work. Okay? And you can see that, for instance, at 2 meters a second, 1 hertz, there's quite a bit of error, and then it drops off fairly quickly as you go to higher sample rates and lower velocities. Now we look at the same table for SSD, and now we get to see the shape of this space a little more clearly, right? So as you increase the speed of the target, then you need to increase the sample rate, right? We see the shape of this curve here, and you look at the edge of that curve. In the feasible region, the error is fairly high, but then as you go to higher sample rates, it really flattens out fairly well. Okay? So there's clearly a trade-off there. So this illustrates that latency is an important characteristic. We also believe that other results or characteristics are important to this, and we're busy working on a different model for error in perception for control systems. And hopefully in the next few months, we'll have some results that we can talk about more openly. Okay, so this is the work of my student Krishna Muva. I'd like to switch gears now and talk about the work of my former graduate student and current postdoc, Deep Samal, on Lidar. So this is a setup that Shaibal and I put together at Georgia Tech. On the left side, you see a flash Lidar camera. On the right side, you see an RGB camera. This allows us to do pairs of capture, as we'll see in a moment. Flash Lidar cameras capture an entire frame at once, okay, in 2 dimensions. A lot of LiDARs that you see on vehicles are scanning LiDARs. Good news is you get 360. The bad news is that it takes time to scan, right? So just as a quick comparison, the flash LiDAR doesn't give you a whole lot of pixels. They're larger in the scene than you would get from RGB, but it runs at a very good sample rate. Okay, Deep did quite a bit of experimentation with this system, and our group of students put together a data set of imagery in areas around Georgia Tech and Atlanta that includes, in various combinations, visible, infrared, and Lidar. So these are visible in an infrared view in front of the Georgia Tech Stadium. We've got these benchmarks on the internet, and our students spent a great deal of effort and damaged quite a few brain cells in order to provide ground truth for this. They had to go through and label these things. Even with tools, it was an extraordinary amount of effort. These students were sitting there for weeks and weeks and weeks labeling these things. But that's what you need to do in order to do research in this area. So, Lidar, for a couple of reasons, right? It has some distinct advantages, but it also has some limitations. If we want to use Lidar for tracking, which is very important in urban scenes, it's also important in other areas, how can we improve the accuracy of a Lidar-based vision system? Okay, so we've got a stream of Lidar frames coming in. The top box is a neural network detector. Okay, so on each frame we're going to detect objects of interest, feed it into a fusion tracker that's going to turn those observations into tracklets. Okay, so if something is obscured for a while, you'll have two tracklets, but it's going to connect up those different frame-by-frame observations. Okay, we can do that, but it's not as accurate as we might like. So the technique that Deep came up with is to use a separate technique in parallel and then compare the two. Okay, decide which one is probably more correct. Feed that into the fusion tracker to generate the tracklets. Okay, so Deep looked at two different alternative sources of detectors. One is model-based, and the other is a self-supervised, fully connected network. Okay, so the model-based algorithm is handcrafted, more traditional computer vision, and the a fully connected network is a simple, fully connected network. Okay, both of these networks are going to be used to create what are known in the computer vision world as foreground masks. Now, foreground in the computer vision world means of interest, pixel or region of interest. In the theater world, foreground means at the fore, and background means at the back, but that's not the case here. Okay. So here's some video. Let's stop this for a moment. So top left is the results of the of the neural network detector. Top right is a foreground mask that was generated by an alternative method, and then the bottom is the final tracker output. Okay, so you can see that the object detector is doing okay, but it's not perfect, and certainly farther back it's where the objects are pretty small, it's not doing great. You can see that the foreground mask detector is detecting certain pedestrians of interest. You then fuse everything together and you get these tracklets here. Even this fused result is not perfect, but it's better than single technique alone. And we'll look at some numbers in a few minutes. Okay? But you can clearly see that of the lower resolution of flash LiDAR, these, to us, they look like people because our visual systems are very good, but there's not a lot of detail there. Okay, so first technique in order to generate this second estimate is the model-based detector. Okay, so we'll take the flash LiDAR stream and generate a depth map out of that, okay, which is just a transformation of the data basically. Then use some heuristics to remove ground points. Ground is can be mistaken for certain things, right? So use some heuristics to do that. do a clustering of that result in order to find objects. Okay? In parallel, going to use background subtraction for temporal components. Background subtraction basically looks for the amount of change in a region, very small change. Classic example is leaves that are fluttering in the wind. You're probably less interested in, but you know, regions that have more significant motion you want to identify as important. Then take those two spatial and temporal saliency paths, combine them, and then generate this foreground mask, which we're then going to use to compare to the neural network detector. Okay, so this is the output of that model-based detector right there. Okay, so it's not detecting everyone, but it's doing a fairly good job of following the things that we detect. And when you see green flashes all over, that's when somebody walked right in front of the camera. Like that. Okay. So this is the fully connected network, and actually what's operating at runtime is down at the bottom here. The top part is the training mechanism. Okay, so we're going to the fully connected network is just going to directly generate a mask saying, I think there's something interesting here and not something interesting over here. Okay? So both methods give us this mask, which we then use to compare and update the tracklets. Basically, if the mask says there's something there and the neural network says there's not, the mask wins. Okay? So it doesn't have to be perfect, but it has to be different, make different types of mistakes from the neural network. How much does all this cost? Well, the model-based method is a little more expensive computationally. So these numbers are on a sort of standard desktop GPU. This is not necessarily reflective of what you'd put in a vehicle, but it gives you a comparison, right? The fully connected network is about half the computational cost of the model-based detector. So how do they compare in results? Well, the model-based is a little better, okay? The fully connected network is a little noisier. So here you can see the model-based result for one frame, the fully connected result from one frame, and you can see there's a lot of stuff in the fully connected network that is not in the model-based result. And if you look at the Lidar frame or the RGB frame, you can see that some of what the self-supervised network is connected to is standing objects like this little pergola that's sitting in front of our building, things like that. Okay? So the model-based detector costs more, but it does a better job. Well, it appears to do a better job. This table tells us that, in fact, it does do a better job. So the supervised only network is up top. Then we have the model-based and then the fully connected. Measure of tracking accuracy is the rightmost column. We can see that the model-based method supplementing the supervised only network does noticeably better. They decrease the false negatives. Both methods decrease the false negatives, but we also see an increase in the false positive rate, okay? Which is the more significant error. Depends a little bit on your application, but in a lot of cases, false negatives are more dangerous than false positives. Okay, so you know, there is a whole bunch of continuing interest in how we do perception in neural network for vehicles and autonomous systems, and we think that this looking at it as a co-design approach is the right way, because we have a complex design space and a lot of trade-offs that we can make. Okay? In the case of control systems, we should evaluate perception based on what the control system needs and not what we need for internet applications. We saw a trade-off space between accuracy and latency. And we also saw how we can use self-monitoring in order to improve the accuracy of these systems. And once again, my graduate students deserve the credit for this. Okay, so thank you very much. I really appreciate your attention.
Thank you very much for the talk. Any question from the audience? Yes, please step up and to the mic.
Thank you for the presentation. I am Shaumendu from Purdue University. So one of my question was, why did you decide on checking the fully connected network, the self-supervised? Like, was it an intention to see how the self-supervised learning will work and give you less compute, or like how do you decide on both of these approaches?
Well, you mean model-based versus the fully connected network?
Yes.
The choice depends on your particular design application, right? If you can afford the model-based method, that at the moment that's doing better. Whether some other, fully trained approach would do better, we don't know yet. But if you can afford it, model-based probably makes sense. If you want to improve your results somewhat, but you have very strong limits on the computation you can throw at it, then the fully connected network seems to be a good approach.
Okay.
Right?
Okay, yeah, thanks.
Yeah.
That was my question.
Yeah, thank you.
Yes.
So it's Arne Hamann from Bosch. So thanks for your talk. I agree very much with the first part of your talk, saying because we are building CPS products, it's very important that the latency is taken into account. And we have a lot of discussions with our control engineers.
Yes.
And the question I have to you is, do you also take into account control methodologies that take into account latencies and delays? Because there's also a whole body of work, which basically is a third dimension in your work, or could be a third dimension.
Well, yes. So this work was done with PID. We've also looked at LQR. The control model, algorithm itself. My gut feel is that looking at the error model associated with that control law is probably the most important thing for us, right? Yeah. Rather than the particular mathematics of how you compute the control output. And if you think about, well, in classical control, right, you've got a Gaussian model for error for the sensor and for lots of other things. We think that a Gaussian model is too simplistic.
Yes, exactly.
Okay. And also let me point out that traditional digital control theory gives us a certain amount of advice on what the sample rate should be for control purposes, but it's often requires experimentation to figure out what's necessary there. Does that make sense to you?
Yes, that's part of it, and there's a lot of interest in our efforts to use uncertainty quantification for this kind of effects. I think that's exactly what you are talking about.
And the question is, what is that uncertainty? What is the form of that uncertainty? And we have some ideas, and stay tuned to this channel. Okay, we hope to have some results in the next few months.
Okay, so let's stay in touch. Thanks.
Thank you.
Thank you. Any other question? Well, actually, I have two questions. So one of the key messages from this morning's keynote presentation was like, not all the errors are same.
Yes, that's right.
So how to factor that into this feedback system that you were talking about? That's one question. And second question is, for certain application like drone tracking, this design space exploration for lower energy or less latency is important, but it sounds like it's very important to add in some kind of real-time formulation there to prevent that lost tracking situation. So is there some kind of research going on there to factor that aspect?
Okay, so first question is about error models. We believe that the error models people use to evaluate, that you see in typical papers are insufficient, okay? Once again, in a few months, we hope to have some results that we can talk about, okay? But I agree that the error models we're using right now are not quite right for these kinds of applications. And so your second question was about cyber-physical systems and real-time systems. Yeah, I think that for a controlled setup like this, the cyber-physical system design aspects are a little more tractable. But when you put it in a, because a drone doesn't have that many different components going on. You've got one camera, and one controller and so forth. In a car, you've got all sorts of sensors. You've got all sorts of other things going on. You've got multiple networks, and that's a big problem. We actually have another project right now on cyber-physical system design for machine tools, where that's sort of a different venue where we can explore some of those issues, but clearly important.
Okay.
Great.
Thank you. So I think key message is to stay tuned for the follow-up
Yes,
research.
that's right.
All right. Any other question from the floor? If not, then let's thanks one more time.
Thank you so
Professor Wu.
much. Thank you for
And
coming.
also, congratulations again for
Thank
this
you.
prestigious award. Thank you very much.
Thank you so much.
Thank you.
Boom.